All right, guys. So welcome back to the wireless channel. And today we're gonna have a talk by Getwar Shepi, who just joined our PhD program this week. Congrats, Getwar. And he has already some interesting result to share with us, which is this work on pilot allocation for MIMO ISAC. So Getwar, thanks very much, and take it away.
Thank you. So today I'm going to discuss about my journal that we submitted last week called Pilot Allocation and Receiver Design for Cell-Free Massive MIMO ISAC Systems. Just to be clear, today we're only going to cover the pilot allocation for the cell-free MIMO ISAC systems, and we will cover the receiver design in another video. I would also love to thank my collaborators, Ryan, Dr. Ando, who just graduated last year, Professor Abreu, and also our industry collaborator, David Gonzalez. Now, without any ado, let me go to the contents that we're going to cover today. So first, I'm going to introduce the concept of the self-free massive MIMO. Then, what is the problem in this wireless infrastructure? Then the system model and proposed solution, and at the end, the simulation results. Now, why what is self-free massive MIMO? Let's see the context of our problem. So the self-free massive MIMO can be illustrated as the figure on the right, where you have many APs that are connected by this backhaul link to a central CPU, and the core idea of self-free massive MIMO is that there are no cells, there are no boundaries, and these APs serve many users at the same time. So this system model consists of K users, M APs, where each of users and APs has one antenna, but of course this model can be generalized to multiple antennas. Now, why cell-free massive MIMO infrastructure is interesting? Well, we have some advantages over the conventional cellular systems, like the conventional MIMO, and we will see also later some results. But some advantages are listed here as higher SNRs with smaller variations, the ability of cell-free mass MIMO to manage interference, and also the coherent transmission of cell-free increases the SNR. Now, if you see the figure on the right, this is a general comparison of three main MIMO infrastructure, the cell-free and the two cellulars, massive MIMO and small cells. As you can see, the blue line, the cell-free massive MIMO, has the best achievable SNR by random UE. Of course, when there are some cases where the massive MIMO has better SNR, but this comes from the fact where the random UE was very close to the huge MIMO array, and that's the only case when the massive MIMO technology is better than the cell-free. But overall, cell-free achieves the best SNR. Now, what is the problem with the cell-free massive MIMO? We're going today to discuss the problem with the channel estimation, more precisely, the pilot contamination problem. So as you know, the channel estimation is crucial for all coherent wireless communication systems. And to do channel estimation, some pilots are sent before the data is transmitted as some reference or known signals. But due to the limited coherence interval, we cannot send pilots for each user, especially when the number of users increases. So we have a limited number of pilots. Thus, the phenomenon of pilot contamination occurs as described by the figure with the red arrows, where both users are using the same pilot. Now, this pilot contamination leads to system performance degradation and bad user experience. And as I mentioned before, this problem becomes even more pronounced when the number of users increases. Now, to quantify our problem, we first have the MMSE estimator as shown by this equation, where we have, okay, so tau is the pilot length, rho is the pilot power, betas are the fading coefficients, and at the denominator we have the noise and the interference caused by the pilots. Now we know that pilots have the property of orthogonality because these come from a orthonormal basis, but these pilots will be reused, and that's where we have the pilot contamination. Now, to state our problem, we express the SINR expression as this big equation here, where we have the desired signal, the total interference at the denominator, where pilot contamination comes from the first term of the denominator. Now, the variance of the channel estimation is described by this bottom equation here, which is this is a variance of the estimate that we saw before. Now, what we want to do is that when we have a limited number of pilots in a self-free massive MIMO setting, how could these pilots be allocated so that the pilot contamination is mitigated and at the same time the pilots can be utilized to perform high accuracy sensing? So we have to be clear that there are already existing methods to produce pilot matrices that are suitable to self-free massive MIMO, but none of them consider any sensing operation. So by considering this, our work is very new, novel, and original. Now, the general formulation that you can find in a paper that considers the pilot contamination problem can be formulated as an optimization problem such this, where you maximize the sum rate or the throughput such that the pilots are contained in a pilot orthogonal matrix, and the P is the assignment solution that needs to be assigned to each user. Now, as you can see, this problem is highly non-convex and cannot be solved in a computationally efficient manner because you had to do an ML search to see which pilot needs to be assigned to which user such that the throughput is maximized. Now, to deal with this, our main idea of the solution is to redesign the pilot matrix such that the sum rate is maximized. But in addition to this, we also constrain the entries of the pilot to unit absolute value or unimodular, such that we can use these pilots to perform high accuracy sensing. Now here, the constraint quantifies what I said, where we have the Fourier transform of each element of the matrix is absolute value 1. Again, this problem is still non-convex due to unit absolute constraint, but for this we can use our tricks from manifold optimization to solve this problem efficiently. Now, why would you use such constraint? As you can see here, why unit modular? Is it already known that for especially in the ISAC area, is it known that for enhancing the sensing performance, you have to constrain yourself or your signals to be on unit disk, and this comes from the very fact that the integrated side lobe level, or as known as ISL, at this case is 0, and this can be proved very easily by using Parseval's theorem, as it can be seen here, where you go, as you know, the autocorrelation RK is the Fourier transform of the power spectral density, and then by doing some manipulation, you can see that by designing the your signals on the unit disk, this sum goes to 0, and thus you have perfect sensing performance, or 0 side lobes. By the spirit of this, we design or we tailor our own algorithm, complex circle manifold algorithm, with a closed form gradient, which makes it efficient, and it's basically composed of 3 main steps, which is retractional manifold, closed form gradient update, and then manifold tangent projection. And at the end, you have your final pilot matrix, which will enhance the total sum rate and sensing performance, which we will see the results soon. Now, it should be mentioned that the new matrix that we designed can be easily integrated in the existing systems by just doing a simple linear combination. What I mean by this is you can go from your original orthonormal basis f to f bar by just doing linear combination of your original f. So that's not a big deal at all. So you don't have to change the whole algorithm in your existing self-free massive MIMO. It's just a linear combination in between these two. Here I show the closed form gradient because, as you saw, the SINR expression, in the SINR expression, you can see the pilot dependencies also in both the numerator and the denominator, and it's not very trivial to solve the closed form gradient. And in this slide, I also saw the complexity analysis and comparison between state-of-the-art pilot methods. So one of the current state-of-the-art method was the taboo search, which has this complexity. And if you compare to the proposed one, you can see that there is only a linear term in addition to the taboo search complexity, but this can be justified by the huge gain in sensing performance that we see. In the other hand, the optimal solution, as you can see, is exponentially increasing. So tau to the power of k, k is number of users, tau is the pilot length. And the random solution, which is the worst, of course, because you just randomly allocate the pilots, is linear. And also the greedy, which does a similar job to random, but considers also pilot contamination. But this is also linear in number of users and APs. But in the table at the left, as you can see, even though the complexity of our proposed idea is not so good, like the random, you can see that we offer both sensing and unique pilot design and reasonable complexity. Now, let's see the simulation parameters of our experiment. And I have to mention that our simulation experiment is very realistic in the sense that we consider a realistic path loss model and also shadow fading for the channel itself. We consider both large scale fading and small scale fading, where for the small scale fading coefficients, we assume only statistical CSI, meaning we know only the statistics of the matrix H. But for the betas, we assume we know this, or we measure them beforehand. This is the pathless model, which comes from some 3GPP standard. And at the table, we have the carrier frequency, bandwidth, noise figure, AP height, UE height, the power of this row, the power of the pilots, the standard deviation for the shadow fading, and then our experiment consists of a square of 1 kilometer by 1 kilometer, and then these distances that come in the pathless model are 50 and 10 meters. To realistically see how far the users are from each AP. Now, before we go to results, I would like to give some intuition about what is happening exactly with the pilot design. If you consider the state-of-the-art algorithms, you have a tau by tau pilot basis matrix where you have tau pilot sequences, each of length tau. So this is a square matrix. And then what the existing algorithms do to assign pilots to user is just so for example, the greedy or the taboo search, take the existing pilots, but just assign to the K users the existing pilot. So this is the same color is reused. In this sense, reusing the same color creates cross interference. In the other hand, my proposed pilot matrix design, uh, you have uh, variations of the same color. So, for example, the first user and the last user are not the same, but quite similar. So there are variations of red, or the third user and tau plus one user are variations of blue. And these variations of colors allow for less cross interference, which means that these are uh, uh, almost orthogonal, not orthogonal because of the dimensions. Now let's go straight to the results. First, I present the result for the sum rate. Here is a CDF of the per user uplink net throughput for uncorrelated shadowing, where you have 20 users and the pilot matrix is 10 by 10, and you need to allocate these pilots to the 20 users. I have two scenarios of APs, so 40 APs and 100 APs. And as you can see, our proposed black man-up solution approaches the state-of-the-art method in sum rate performance, which is the taboo search, and outperforms by far the random and the greedy algorithms. It is worth of mentioning that here we consider the overhead from channel estimation, which is this term, and uh, yeah, this I already mentioned. So next we present the rate for varying pilot length. So it's the same metric, but I take the median per user uplink net throughput. And here we have 40 APs and 20 users, and I vary the pilot lengths from 10 to 20. And as you can see at 20, you have no cross interference because you have 20 users and 20 pilots, so you can just assign one for each of them. But the interesting point is in between, right? And again, here we see that we're very close to the state-of-the-art, almost optimal taboo search solution. And again, by far, we beat random algorithm and the greedy. The other plot was for varying pilot length. Now we vary the number of UEs for a fixed number of pilots. And here we have 40 APs and 10 pilots. And again, here we only cover the overloaded scenario, meaning you have 20 and UEs, which is a factor of 2 overloading, and then to 40, which is a factor of 4 overloading. That's why the rate decreases. Again, as you can see, over all these overloading scenarios, our proposed algorithm is very close to the taboo search state-of-the-art algorithm and beats by far the random and the greedy algorithm. Now we go to the sensing experiment. First of all, without doing any sensing, we just plot the a periodic autocorrelation function for the considered pilot, which here I consider three of them, coming from the greedy algorithm and the taboo search algorithm. And as you can see, both of them have a very fat autocorrelation, while the man-opt algorithm, even for a small pilot length, just 10, has a very peaky autocorrelation, and this will scale with the number of pilots. Even though the range resolution here is very big because it depends on the bandwidth, and the bandwidth used by the cell-free systems is 20 megahertz, if I'm not mistaken. But this doesn't make our result bad. It just makes our problem even better, because when we have a bigger bandwidth, then our range resolution will be even lower, and we can perform even more accurate sensing So for what I'm trying to say is that for the sake of the fair comparison, the bandwidth is kept the same at the state of the art. Now, I also have a ranging estimation problem, but I cannot see it here. Let me just clear this. Okay, here. Sorry. Okay, here we have a range estimation experiment for dual targets. So we have one target at, I think, 7 meters and the other at 90 meters, and we use a pilot length of 64 pilots. And as you can see, using our MANOP pilots, we can accurately sense the target, but using the other pilot, which is the blue line, you cannot sense the targets precisely for the same reason that you saw in the other slide, because the autocorrelation function is very fatty, and as you can see here, the side lobes are very tight. With this, I close my presentation, and thank you for your attention, and I look forward to your questions.
Thanks so much. Very nice. Any questions, guys?
So I have a couple questions.
Yes,
Go ahead.
So on page 18, could you go to page 18?
I cannot see. Okay, here.
Yeah, so it's just a question regarding at pilot length tau equals 20, we should have unique pilots for everyone, right?
Yes,
But why for the greedy and random the performance drops after?
I think this is because this is normalized, so it drops a bit.
Okay.
So if I remember correctly, I normalized by the number of users, because this is per user, and
Mhm.
uh, even when, because you have to realize, even when you have all the pilots, the random algorithm will still make mistake, right? It's not that smart to allocate the best one to each user.
I see, I see.
So
Okay.
it's a for the overloaded case, the greedy and random are not so good. But this is not so interesting, right? Because the random and the greedy are really needed when you have a really overloaded scenario, like you have
Exactly.
hundreds of users, and this is justified also by the complexity, right? Because the complexity of these
Mhm,
two algorithms is very low. So
mhm. Okay, okay. That was just a curiosity why that was the case. And the second one is for page 20. If you go to the ranging, um, oh, maybe it wasn't 20, maybe one before.
you mean the other figure, the autocorrelation?
Yeah, maybe it was the other, but in here it's also fine. This is fine
Yeah.
as well. Okay, so the question is, it says the tau here, the pilot length plays a role in improving the PSLR of the ambiguity function, right? Could you just
Yes.
elaborate on how that is the case? Like how if you have a specific relationship or
So I also had the plot for this, but I didn't include this. Maybe this was my mistake. But if you see the expression for the ISL or PLSR, which is the integrated side lobe ratio or the peak to side lobe ratio, you see that with increasing elements, your side lobe level will go even more to the negative dBs.
I see. So it will be you will improve on the peak to silo ratio when you have
Yes,
a longer tau, right? Okay, okay.
I will improve because mine
Okay,
are the
exactly,
unit
exactly.
circle, but the other guys are useless.
Exactly. So I just wanted to highlight that. So then when we have a longer
Yeah.
tau, then in
Yes. So
theory,
yeah.
at limit, it will be really flat, or it will look quite flat, right? The side lobes, and you'd get a very nice peak in the middle, right?
Yes. True.
Okay,
Because
perfect.
yeah, this
Okay,
is only for 10. So
exactly.
it scales with the number of pilots.
Exactly. And this is only with the proposed method because the other ones do
Yeah.
not have this
But
characteristics.
you have to realize that you cannot use very long pilot sequences
Yeah,
because
of course, yeah.
as I said here, as I said here, uh, there is a trade-off, right, between pilot length and
Mhm.
rate. So
Of course.
if you use a very long pilot, then the rate will also decrease. So
Okay.
this is actually another problem that we discussed internally, which is to find the optimal trade-off. But this is another problem.
Okay, thank you. That's it for
Yeah.
me.
Thanks, Eric. Anybody else? Maybe while you think, I do have one question. Can you bring us to the equation where you model the interference as a consequence of pilot contamination?
To the equation?
Yeah, when you model your pilot contamination, right? You should have a receiver signal model where you are matching your well, this is already in terms of
Yeah,
SINR, but that's good
yeah.
enough.
These are like collected. I don't have the I
Yeah,
have it in the
that's fine.
paper, but not here.
That's good enough. My question is the following. So if I understand correctly, looking at this equation, it is assumed that everybody's symbol synchronized, right? Meaning all the pilot sequences are given to the users and they are used such that all the signals are arrived in synchronously, correct?
Yeah, this is
Meaning
a
I have
assumption.
here, this does not include the case, for example, I am a bit one, let's say one receiver is one transmitter is one symbol delayed with respect to the other, which can happen simply, for example, because of distance. One guy is very far away. Is this what would happen if this took place? Meaning you'd have here not only a sum, which is the symbol synchronous cross correlation, but also several sums for all possible kind of cross correlations that are not synchronous.
Mm-hmm.
Have you thought about that? In other words, well, at least I think it would make sense to consider at least one symbol, one level of symbol synchronous. So one symbol delay. And yeah, I'm just wondering how the design would be
No,
robust
this
or not.
I never considered. I always assume this is like
Okay,
coherent
okay,
and
right. Okay,
synchronized. But this is another research direction, I think.
yeah, okay. So yeah, maybe it could be extended into that case.
Yeah.
All right, anybody else? If not, well, the video is long enough. Actually, it's already 18 minutes or so. So I thank you very much, Gatoir, and yeah, I'll welcome everybody back to the Wireless channel next time.
Thank you.
Thank you.
Cheers. Bye.